This is the section 1.3 video on transformations of functions. There is a bit of vocabulary here, so please make sure you're aware of this vocabulary. A transformation is the movement of objects on a coordinate plane or how graphs change. The rigid transformations are transformations that do not change the shape of the original graph, only its position or orientation, which includes shifts and reflections, as well as rotations. Non-rigid transformations change the shape of the original graph, meaning like the size. So it may still be a parabola, but now it's a bigger parabola. That is considered a non-rigid transformation. If you have time to follow along with the exploration on Desmos, I would recommend it. See how the graph is impacted when we just have f of x minus 2. Hopefully you guys can see this well enough. As you can see, the red one is the one that has been altered. And of course, it is just shifted down 2. And then if we switch which one we're viewing to where it's inside the function, this one does not just shift it down. This one, of course, shifts it to the right 2. You can go through these if you would like. The plus 2 moves it up when it's on the outside, but when it's on the inside, it actually moves it left 2. The negative on the outside reflects that across the x-axis, but when it's on the inside, it reflects it across the y-axis. And there are some of these others down here, the 2, the 2x, the half on the outside, the half on the inside. Add in these, so these, of course, have essentially opposite effects of one another because one's plus and one's minus if you look at these colors together. Now remember, everything on the inside is kind of the opposite of what you would normally expect. When we have a negative on the outside here, that reflects across the x-axis. I think about this one like everything on the outside is vertical, and so when it's a reflection on the outside, it's a vertical reflection. It starts up high and goes down low, or it starts down low and goes up high. However, when the negative is on the inside of the function, like here, this is a reflection across the y-axis. And again, I think of that similarly. If this is the y-axis, it's actually flipping to the left and right, which is what you would expect from the interior things. So essentially, each point here, we would multiply the y of it by 2, because this says 2 times y, essentially. So instead of being at -6, -8, this one would actually be at -6, -16, which is clear down here off the graph. It's already on 0, so if we were to multiply that by 0, there's really nothing that changes, right? So both the original and the transformed point actually stay right there on that same spot. So then for this one, our y was 2, which multiplying by 2 gives 4. This one also stays there. Multiplying 6 by 2 gives us 12, so approximately there. This would be at 4, 12. This one is at -6, -16. And this one comes out to 4. However, the majority of this really stays the same, though. The shape is very, very similar. It has just been stretched out. So how is the graph impacted? A vertical stretch by a factor of 2, and it is taller. So when it's on the inside, okay, so this one, when it's on the outside, it gets twice as far away from the x-axis. However, when it's on the inside, we actually want it to go twice as close to the y-axis. So these original points here, in this case, are going to move toward the y-axis. So this one was at -6. We want it to be twice as close, so it should be at -3. This one should move to -1. This one, of course, is already on the y-axis. It can't get any closer. All of those points just kind of move in towards this y-axis. So now that those points are twice as close, you can see this. This is what we call a horizontal shrink by a factor of 2. And you can see that this graph gets skinnier, pulls it in tighter. Now if the 1/2 is on the outside, so this is similar to what was happening here, except for that this time it's dividing instead of timesing. So in this case, it is going to get twice as close to instead of twice as far away. So 2 made it go further, but 1/2 will bring it in towards the x-axis. And the reason for that is the y is essentially getting divided by 2. So as we do these, we can think about them going 1/2 as far away. Of course, if you're already on it, you can't get any closer, so those stay. And the others kind of come fill in here. Vertical shrink by a factor of 2. And this one, of course, gets shorter. So of course, when we had the 2 on the inside, it was getting twice as close to the y-axis. So when we have a 1/2 on the inside, it's actually getting twice as far away. So we do the same thing here. We have our original points, and we need to adjust them to be twice as far away now. This one ends up out here at -12, -8. This one ends up at -4. This one's already there, it can't move. This one ends up at +4. This one ends up at +8. And this one ends up at 12. So this will be at 12, -2. This one is a horizontal stretch by a factor of 2. This one gets wider. So hopefully that's a good refresher to you guys about how the graphs transform a little bit. Go over some of these where these points ended up. So this one ended up at -3 because it was 1/2 the distance. This one ended up at -12 because it was twice the distance. And that's going to continue to be true. That'll be -2, -1, 0, 1, 2, and 3. Whereas if it's the 1/2 on the inside here, so this was getting 1/2 as far away, this one's going to be getting twice as far away. So this will be -8, -4, that one stays at 0, that's 4, that's 8, and that is 12. Okay. So generally speaking, this is what's given to you. I hardly ever use this H and K notation. The reason I don't like the H and K notation is because it implies that there's either a vertex or a center, which is not always the case. So I prefer to use the letters C and D. So A, we have talked about, it controls our vertical stretches and shrinks. And we can tell the difference by knowing if A is greater than 1, it is a stretch. However, if A is a fraction or between 0 and 1, it is a shrink. And we'll also do D right now. This is going to be a vertical shift. So it will either be up or down, depending on if it is a positive or a negative. One last thing I did want to add is that if A is negative out here, if this is a negative, that is a reflection across the x-axis, and that is independent of the size of A. You'll notice that A is never talked about as being a negative because this negative is treated very separately because it's a reflection across the x-axis. Okay. And then we also have our B's and our C's in here. So the B value, similarly to A, does horizontal, stretches, and shrinks. And it is a stretch when B is between 0 and 1, meaning it's a fraction or not quite 1, and it shrinks when B is greater than 1. And again, that's the opposite of these. I want you guys to notice those are opposites. Okay. And of course, these ones could also have a reflection, but it is treated completely independently. So if there's a negative with B, then it is a reflection across the y-axis. And last but not least, we have our C value, which is also a shift. It is a horizontal shift, which can either go left or right. And just like everything else on the inside is opposite, it goes left when it's a plus and right when it's a negative. So let's go ahead and identify some transformations using a point. So if you're given this point and this function, you have all the information you need to find where the new point will be after the transformation. So we're going to look here and see that this is a negative. Remember, that's a reflection across x. This plus 7 here is going to move us left 7. And this minus 4 here will move us down 4. So as we do this, we need to recognize what these transformations affect. Left and right will affect your x. Moving down will affect your y. And reflecting across x also affects your y. Because if this is your x-axis and you were up here, now you're down here, your x will remain the same. It's your y that's going to change. So we can think about this way and say if we start at negative 3, 2, and we reflect it across the x-axis, then our x will stay the same, but our y will become negative. Then if we move it left 7, that is going to affect our x value by making it smaller by 7, but our y value will be unaffected. So this becomes negative 10, negative 2. And then the last transformation is moving it down 4, which will not affect our x value, but will affect our y value. So our ending point then will be at negative 10, negative 6. Now you could have done those graphically also, and if that is how you choose to do them, then that is just fine. You would simply plot your point of negative 3, 2, and perform the same things. The next section got a bit split, so I apologize, but this is supposed to be your original f of x, and then it would like you to graph f of 2x as well as 2f of x, so as to compare the two. So we will go ahead and do that, again with the 2 inside. That means that it would like us to be twice as close. So we take this point by point, and we see that in order to get twice as close from this point, we need to remain on the negative 2 this way, but we need to come in more to negative 2 also, because half of 4 is 2. This point will remain where it was. It cannot get any closer to the y-axis. And finally, the point that was on 2 will come into 1. And that is your graph. Similarly, when we have the 2 on the outside here, that will affect our y values instead, and our y values will get twice as far away. So this time we're going to remain on the negative 4 for the x, but the y should drop down to negative 4 also. The middle point there will be up at 4, because twice of 2 is 4, and twice of 1 is 2, so this will be there. One thing that is very interesting and worth noting is that the slope of this line is 2. The slope of this line is also 2, whereas the slope of this line was only 1. So in both cases, it doubles the slope, but it doesn't necessarily double proportionally, because this is not in the same point as this. However, it does increase that slope in both cases. Okay. Similarly, this one was -1/2, and then it becomes -1 because they both get doubled. So let's try another one out. This one is asking us to reflect the graph over the x-axis and then translate down by 3. So the reflection over the x-axis would simply take our parabola as it sat and flip it upside down. Then to translate it down by 3, each of those points would now drop down by 3. If we translate the graph down by 3, then we would start with the same parabola and we would simply drop it down 3. Then it's asking us to reflect over the x-axis. So in order to do that, we would need to take some points and more individually reflect those to result in this red parabola. Now, hopefully you guys noticed that these transformations were identical transformations. However, the order matters. When we use the different order, we do get an end result that is not the same. The end result here is the red one. The end result here is the purple one. They are not the same graph. Order absolutely does matter. The general rule would be that you go from left to right. An acronym that may be helpful to you is STRESS. It means you do your stretches and shrinks first, then you do your reflections, and then you do your shifts. The reason that works is because the reflections and the stretches are always going to be on the left, and the shifts will always be on the right. So if that helps you, you can remember that is the order they should go in. So now we have another graph, and it would like us to sketch these transformations. There are 2 methods listed here. The first would be to list the transformations. The first thing that I will always do when I see stuff like this is to put the x where I want it. I prefer the x to be first. Another thing I'm noticing is that there are actually 2 distinct values here. There's a -1 and a 1. Remember, when you have both a b and a c, you need to factor out that first one. Otherwise, your shifts will not be correct. So what I see here is actually a reflection across the y-axis. And then there should be a shift to the right one. Okay. Using the table method, what this is saying is instead of looking at the graph as a whole, let's look at each individual point. So originally, these were our x and these were our y's. However, if we plug the x into this new format, it's going to be affected differently. So, of course, the reflection across the y-axis would turn all of our x's negative, but would keep our y's intact. And then if we were to move right 1, that would add 1 to each of our x's, but again, would leave our y's unaffected. So these new points are what are going to stand. And I hope you guys recognize that when you do 1 minus x, well, 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 4 is negative 3. And our y remains the same. And on the next page, it does want us to go ahead and graph that. So the first thing I am going to do is look at these points. I think the table points are a little bit easier in this case. So we should be at the point 1, 0, the point 0, 1, and the point negative 3, 2. This will be what it looks like. Okay. However, you could have done this with the graphing method also. I hope you guys realize if this was the original, we reflect it first and then shift it to the right one, it ends up the same. So that's why those are useful. I hope that helps you visualize as well as be able to do the algebra behind it. Okay, here's one where it just gives you the function and says to sketch it. We do this by understanding what transformations are happening. So the parent function here is the absolute value. So I'm going to start off with putting the absolute value function on here, just so that we have a point of reference. Looking here, we have a 1/2 that is on the outside, which tells me that is a vertical shrink by a factor of 2. We also have this +1 on the inside, which will make it move left 1. And we have a -5 out here that will move it down 5. The first thing I would do, again, we're supposed to move left to right here, is I would find some points that are useful. Useful is relative. However, I know that I need to divide by 2. So the most useful ones are going to be even, because evens easily divide by 2. So 10 divides by 2 down into a 5. 8 divides by 2 down into a 4. 6 divides by 2 down into a 3. 4 divides by 2 down into a 2. And 2 divides by 2 down into a 1. This line goes here. And you could do the same thing on this side. However, I'm going to use my knowledge of the absolute value function to recognize that these need to be exactly reflected of the others. So if that's helpful, you can always do that. And then it needs to move left 1. And then lastly, this needs to move down 5. And there you have your transformed absolute value. The purple one is the final. The next chunk or type of problems is about writing transformations when given verbal descriptions or written descriptions. So the first thing to note is that you're given a parent function of the square root of x, and then we are given 3 separate transformations to perform on that function. Here is how you do this, as well as how you should work for doing this. So the first thing we're going to do is recognize that we need to horizontally compress by a factor of 2. So compress is another word for shrink. So horizontally compressing by a factor of 2, in this case, means multiplying by 2. So we are going to take f of 2x. That's how you horizontally compress. And of course, we're going to actually do that with our absolute value function as well. So there needs to be a 2x on the inside there. The second step is to shift up by 1 unit. So shifting up by 1 unit would take this f of 2x that we have and add 1 on the outside of it, which of course would result in the square root of 2x still being present, but having a +1 on the outside of that function. The third shift is supposed to be a shift right 3 units. Of course, right and left go on the inside with our x. So we would have our f of 2. We need more parentheses here, however, to ensure that our shift is correct. So this would then become the square root of 2 multiplied by the quantity of x minus 3, and then the entire function would have a plus 1 on the end. So to make our answer more clear, our g of x that we have now obtained would equal the square root of 2x minus 6, and then we add 1 at the end. All of these are very similar. I am choosing not to walk through these in the video, but they are on the notes document that is posted. So please feel free to check there for a more complete set there. However, they are done in the exact same manner as this one. This function very clearly started as an x squared function at some point because it's a parabola. So if we are looking at it as if it's a transformed parabola, the first thing we need to notice is that our vertex has moved. Our vertex has moved down 3 as well as left 2. So with that, our vertex moving would alter our equation. So if it starts as x squared, to move it left 2 would add 2 on the inside, and to move it down 3 would subtract 3 from the outside. I think those are fairly obvious and intuitive. However, there are some stretches in here also, and I can tell because if we were to take this parabola, this original parabola, and only move the vertex, that still does not perfectly line up with the function that we are looking at. So what's happened here is that somehow this point has been moved to here. Now, this is actually two different stretches. It has a vertical and a horizontal component. The easiest way to see this may be if we looked at a table of these values of this transformed parabola. So typically in a parabola, from the vertex you go up 1, left 1, up 1, right 1, and there are going to be points on both of those. Or you could go left 2 and up 4, right 2 and up 4 every single time. However, that's not what is happening here. We're actually moving left 2 and up 2 in order to get to our next quote-unquote nice point. So instead of going 1 and 1, we're going 2 and 2. So the first thing I'm noticing is that we are having to move a little bit further this way and further this way. That tells me that there are two stretches here. Both of them are doubling. Okay. So on the outside, that's fairly easy. You just throw a 2 on the outside for that stretch. No big deal. However, because we also had to move left 2, this is also going to bring this into play. And this requires that we have more parentheses. So 2 times by 2, x plus 2, squared minus 3, could simplify into 2x plus 4 squared minus 3. And this is what I would like to see. This one is very similar. I would start by recognizing that this is an x squared function, or sorry, the square root of x. And then it has very clearly been reflected but then it has also been shifted up as well as to the right. So we start with the square root of x, then we recognize that it has been reflected across the x-axis, which would put a negative out in front. Then we recognize that it has been shifted up 3, and then it has also been shifted to the right 1, which would give us this equation.